Hello. So welcome to lecture 2 of our Biomath 203 preceptorship. So my name is Ben and we will be doing graph clustering today. Okay, as a reminder, the notes for this lecture as well as the previous lecture will be available online on this website. It's github.com/biona001/teaching. Okay, so previous lecture, we basically did a bunch of inequalities for proving these probability bounds, right? Today, we will really sort of return back and try to do a little bit more probability stuff. Just to get people started. So let's begin with a review of clustering, okay? So sometimes when you have a bunch of nodes in a graph, maybe this comes from a data, it is natural to group a bunch of different nodes together, right? In this case, this is pretty obvious that I drew it, that these nodes should go together. Sometimes it's obvious, sometimes it's not, and maybe you can have higher dimensional data, right? You have like n dimensions, and you want to cluster those data. So there are many algorithms that are developed to do this kind of task. For instance, k-means. So this is the first algorithm that people usually learn for clustering. There are also hierarchical clustering, and it's kind of similar to k-means. So what these algorithms require is a data, right? So these are the nodes. They reside in some space, Rn, and they also requires a way to measure the similarity between nodes. So let's say you have these two nodes. There's some distance. This is node I, this is node j. This is the distance between node I and j, right? And maybe this is node k, and then there's a distance between node k and I, node k and j. So the typical way for people to do these kind of clustering relies on Euclidean distance, right? Or any kind of distance you want. So today, we will be learning a new kind of distance. It's called the Euclidean Commute Time Distance. That will sort of be a new way of clustering things. And it's not a new algorithm, right? It's just a new metric for measuring the similarities between nodes. So the virtue of this new algorithm is that, let's say you have some graph that looks kind of like this, right? I don't know, maybe this node connects to this node over here, and then you have something that looks like that, whatever. Okay. This new Euclidean commute time distance, Euclidean commute time distance. It measures, it takes sort of connectivity into account. So if you have this node over here and you want to measure the distance between this node and this node, if there are many different ways to get from this node to this node, between these two nodes, the distance will be smaller. And even though the physical distance may be longer, whatever that means, right? So this is the main idea for using the Euclidean commute time distance, because it takes connectivity into account. Okay, so before we start with the real thing, we will just give a brief review for k-means clustering, because we will use k-means as an algorithm to illustrate the effect of this new distance metric. Okay, so this is review. K-means. So step 1, you randomly initialize cluster centers. Initialize cluster centers C1 all the way to CK as cluster centers. So you need to know what K is beforehand, and people usually do that by maybe cross-validation or something, I don't know. So step 2 is you assign every node in your whole graph into the closest cluster center based on the Euclidean distance. Assign every node in graph to nearest cluster, nearest CI using Euclidean distance. Okay, so Euclidean distance, right? Let me just remind everybody, the distance between two vectors, x and y, this is equal to the difference between every single dimension squared, right? It's if your vector is nd, and then you add it up all up, and then you take the square root. Okay, this is the Euclidean distance, or also called the L2 norm or something, right? Maybe it's some other field. So this is step 2. And then step 3, after you compute all the clusters membership, you recompute the cluster centers. Recompute C1 through CK by minimizing within cluster. Within cluster variance. Well, what does that mean? That means, let's say you have this huge thing that you all say every one of these nodes belongs to cluster 1, right? Then you wanna pick some cluster center that sort of is in the middle of all of these nodes, right? So maybe like right over here. So maybe this is the new cluster center, okay? And then C1 will be equal to this point. So that's also very straightforward. It's also, maybe people call it the centroid something. It's just the mean of all of these data points. And step 4, repeat 2 to 3. Okay, let me just put this smaller so people can see what 2 and 3 is, until cluster memberships stops changing. Okay, so very straightforward. This is what typical k-means clustering is, and I'll see you